Good morning, students. Welcome to Bindu Dhadwal Chemistry Lessons. We are doing the chapter Polymers. In our previous video, we have talked about some commercially important synthetic polymers. Let us recapitulate. Addition polymers were of different types. Polythene, again categorized into low density polythene and high density polythene. Polypropylene, this is also addition polymer. Polystyrene, addition polymer of the type having monomer unit C6H5CH double bond CH2. Then we had polyacrylates, which were further divided into polyacrylonitrile or Orlon, polymethyl methacrylate or PMMA, polyethyl acrylate. Then we did polyhaloolefins. These were of three types: polytetrafluoroethylene or Teflon, polymonochlorotrifluoroethylene or PCT, Fe, and polyvinyl chloride PVC. Then in the condensation polymers, we did polyesters, which were of two types, sterylene and glyptal. We did polyamides, all having the amide linkage. Here it is the ester linkage, COO. Here it is the amide linkage, CONH. Then these were of these types, nylon 6,6, having two monomers having 6 carbon each, hexamethylene, diamine and adipic acid. Then nylon 6 was a polymer of only one monomer, caprolactam. Nylon 11, then nylon 12 having a monomer of 12 carbon atoms, and nylon 2, nylon 6, a copolymer having the two monomers, one having 2 carbon atoms, other 6. Then third type of condensation polymers were formaldehyde resins. These were further of 3 types: phenol formaldehyde, which is also known as Novolac when it combines linearly to form a polymer, and Bakelite when it combines in a 3-dimensional network form. We had melamine formaldehydes, and we had urea formaldehyde resins and polyurethane. These we have done in our previous video. Today we'll be talking about rubber, its different types, and synthetic biopolymers. So let's begin with rubber. Natural rubber is obtained in the form of colloidal suspension of rubber in water and is called latex. It is present in rubber trees, which are mostly located in tropical and semi-tropical countries such as South America, Sri Lanka, Malaysia, Indonesia, and southern part of India. From the rubber tree, latex is collected by making an incision in their bark. Chemically, natural rubber is a polymer of 2-methyl-1,3-butadiene. 2-methyl-1,3-butadiene. All the double bonds have cis configuration in the polymer, so it is also called cis polyisoprene. So this is in common system, it's called isoprene. When it's polymerized, it's called polyisoprene, which is in cis form, so it's called cis polyisoprene. So this bond breaks from here, one electron comes here, one here, homolytic fission occurs. Similarly, this bond will break and one electron comes here and one here. These two electrons join to form a double bond here, whereas the electron which comes here is bonded to another molecule of isoprene, and the electron which comes here is used in making bond with next molecule of isoprene. So we have a double bond here and single bonds where there was double bond earlier, and these are the points of linkages. This is cis polyisoprene. The high elasticity of natural rubber is due to absence of polar groups in the cis configuration. about double bonds. These do not allow the polymer chains to come closer, so only weak van der Waals forces are present. Since chains are not linear, they can be stretched like springs and exhibit elastic properties. In order to make rubber more durable, we heat it with sulfur. The sulfur forms cross linkages between two isoprene units, polyisoprene units, and make it more durable. The sulfur linkages can be present through the double bonded carbon atom, or it may be present in the methylenic carbon atoms. The process of polymerization is slow. To accelerate it, organic compounds such as diphenylguanidine or mercaptobenzothiazole or zinc dimethyl dithiocarbamate in 0.5 to 1% can be used. In their presence, the vulcanization can be carried out at low temperatures. The activity of accelerator can be further improved by adding a small amount of zinc oxide or carbon black, which are called fillers. Vulcanization has vastly improved the physical properties of natural rubber. So a rubber heated with sulfur is called vulcanized rubber. Vulcanized rubber is better than the natural rubber in being more elastic, having less water absorbing tendency, being more resistant to oxidation and towards organic solvents, and the cross-linking of chains makes the synthetic rubber more stiff. It can withstand wear and tear better than the natural rubber. Because of cross-linking, stiffness is introduced, and as a result, other physical properties of rubber are also influenced. The extent of stiffness depends upon the amount of sulfur added. A rubber containing 5% sulfur is used for making rubber tires. Containing 1 to 3% sulfur is soft and stretchable and used for making rubber bands and tubes. A rubber containing 3 to 10% sulfur is used for making tires. A rubber containing 20 to 30% is hard rubber, and it's hard and used in synthetic plastics. Sulfur is also employed for making cases of batteries, etc. Vulcanized rubber has the following improved properties over natural rubber. It is hard and non-sticky. It has higher elasticity, which remains over a wide range of temperature. It is not oxidized readily and exhibits the same behavior in all weathers. It's quite resistant to attack by organic acids. There are synthetic. We can also make rubber synthetically. This synthetic rubber, depending upon the monomers used, is of 4 types: neoprene, Buna S, Buna N, and Thiocol. Where rubber was the polymer of 2-methyl-1,3-butadiene, neoprene is a polymer of 2-chloro-buta-1,3-diene, which is also called chloroprene. When it is polymerized, it forms neoprene. So, neoprene is a polymer of 2-chloro-1,3-butadiene, chloroprene. On polymerization, in the presence of traces of oxygen, it polymerizes into neoprene. It's a homopolymer. Neoprene is thermoplastic polymer and is a synthetic rubber. Though it is inferior to natural rubber in some of its characteristics, it's superior in its stability to aerial oxidation and in its resistance to oil, gasoline, and other solvents. So neoprene is used in manufacture of containers for storing petrol, oil, and other solvents. In making neoprene belts to be used in coal mines, and they do not catch fire. In making hoses, shoe heels, stoppers, etc. Neoprene is used. Next is Buna S. It is a copolymer of 1,3-butadiene and styrene. It's polymerized in the presence of sodium, so the product formed is called Buna S. The word Buna S, the Bu means buta-1,3-diene. Na means sodium or natrium, in whose presence polymerization occurs, and S means styrene. In Buna S, the intermolecular forces are very weak. That is why it's soft and elastic. Buna S is a synthetic polymer and is popularly known as SBR, that is styrene butadiene rubber. It is quite tough and less tensile than natural rubber. It's used in the manufacture of tires, for making rubber soles, belts, hoses, floor tiles, etc. Buna N is a polymer of buta-1,3-diene and acrylonitrile, which is polymerized in the presence of sodium to form the polymer Buna N. It is resistant to action of petrol, lubricating oil and organic solvents, and is used in making oil seals and tank linings, etc. Thiocol is a polymerized product of ethylene chloride and sodium polysulfide. So ClCH2CH2Cl is ethylene chloride, NaSSNA is sodium polysulfide, and these combine to form thiocol rubber. So the Na of sodium polysulfide and Cl of ethylene chloride will combine to form NaCl. Similarly, this will also react with adjacent and the three will join to each other to form sulfur linkages. This rubber is called thiocol rubber. It's chemically inert to all chemicals and used in hoses, tank linings, engine gaskets. It can also be used as rocket fuel on mixing with a suitable oxidizer. Copolymerization is the process when two different monomer units combine together to form a polymer. Now, the synthetic polymers are resistant to heat and chemicals like acids, bases, and oxidizing agents. Their inertness is responsible for synthetic applications, but this has created alarming environmental problems, and they are mostly non-biodegradable, and it's very difficult to dispose of the polymeric waste like polythene bags, broken polythene pipes, etc. So the efforts are being made so as to make polymers which can be degraded biologically. So we have seen that natural polymers like polysaccharides, proteins, nucleic acids, they decompose or hydrolyze in the presence of different enzymes and are biodegradable. So efforts are on to make synthetic polymers behave in this manner with characteristics similar to biopolymer. So then they will be called synthetic biopolymers. They are then biodegradable in nature. For example, aliphatic polyesters are biodegradable in nature. Some other examples of biodegradable synthetic polymers are polyhydroxybutyrate, polyhydroxyvalerate. It's a copolymer of these two compounds, 3-hydroxybutanoic acid and 3-hydroxypentanoic acid, one having 4 carbon atoms and one having 5 carbon atoms. So these, when to combine, they form a ester linkage and a polyester is formed. This is polyhydroxybutyrate co-polyhydroxyvalerate or PHBV. The properties of biopolymer can be varied by adjusting the relative proportion of monomer hydroxy acids. It has found utility in packing materials for orthopedic devices and capsules. You must have taken capsules in which the medicine is placed inside a plastic coating. This plastic coating is made up of BHB. When a drug is put in the capsule of PHBV, it's released only after the polymer gets degraded, so it slows down the release of medicine. It also undergoes degradation in environment with the help of certain enzymes, so it's biodegradable. Nylon 2, Nylon 6 is another biodegradable compound obtained by copolymerization of glycine and epsilon amino caporic acid or 6-amino hexanoic acid. So the OH of glycine and H of amino caporic acid will combine to form water, and the polymer so formed is called nylon 2, nylon 6. So generally surgeons use nylon 6 threads for stitching wounds and cuts, but these are non-biodegradable. They have to be removed after some time. Nowadays they are being replaced by this nylon 2, nylon 6, which is biodegradable and dissolves on its own, and there is no need to remove these stitches. Another biopolymer is PCl, or polyepsilon caprolactone, or 6-hydroxyhexanoic acid. It's obtained as a result of chain polymerization of 6-hydroxyhexanoic acid. On heating, it gets converted to polyepsilon caprolactone, or PCl. Polyglycolic polylactic acid, also known as dextrone, is a copolymer of glycolic acid and lactic acid, and is commonly known as dextrone. It's a polyester used as sutures for stitching wounds after operation. These are also dissolving stitches. They will dissolve within a week's time. Actually, the polymer gets degraded within the body as a result of hydrolysis and forms small molecules which are of non-toxic nature, so they can be excreted by the body without causing any harm to the body. This is glycolic acid, OHCH2COH, and this is lactic acid, OHCHCH3COH. On polymerization, they form polyglycolic polylactic acid, or dextrone. Though biopolymers have a wide range of applications, but they may not compete cost-wise with the synthetic petroleum-based products or polymers. The need of the hour is to pay more attention on plant genetic fermentation and purification technologies and devise ways and means to reduce manufacturing cost. A day is not far off when these biopolymers will replace the traditional petroleum-based synthetic polymers, most of which are non-biodegradable and major source of pollution. The advantages of biopolymers are they have several functional uses. They act as stabilizers, thickeners, binders, dispersants, lubricants, adhesives, and even drug delivery agents. Since biopolymers are degradable and are from renewable resources, they have a major scope in industries such as cosmetics, pharmaceuticals, packing papers, textiles, etc. Because of their unique physical and chemical properties, these are utilized in the manufacture of framework from which huge structures can be developed to be used in architecture. In addition to these, they have a wide scope in fields like tissue engineering, food additives, biodegradable plastics, and many more. Just to summarize, rubber can be natural rubber and synthetic rubber, which is of 4 types: neoprene, Buna S, Buna N, Thiocol rubber. And biopolymers are polyhydroxybutyrate, polyhydroxyvalerate, then nylon 2, nylon 6, then polyepsilon caprolactone, and polyglycolic polylactic acid, or dextrone. So that is all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.